Black holes erase matter in a way that makes it vanish from view. Yet the paradox says something essential survives in some form, simultaneously gone and existing. The black hole paradox, the mystery of matter disappearing and existing at the same time. In this video, we pull back the veil on how information could endure at the edge of nothingness, and what that means for reality itself. Join us as we connect event horizons, quantum rules, and Hawking radiation to reveal a puzzle that redefines what we mean by existence. The paradox in brief. Hawking radiation suggests black holes lose mass by emitting a thermal spectrum. The radiation appears featureless and unconnected to the specific quantum state of matter that formed the hole. That makes the apparent disappearance of information troubling. In short, the paradox asks whether information is truly lost or merely hidden in subtle correlations. From a semi-classical viewpoint, the interior beyond the horizon seems inaccessible, and when the hole evaporates, the information appears to vanish. Quantum mechanics, however, demands unitarity, meaning the information must be recoverable in the radiation or elsewhere. A concrete intuition is that a book falling into a hole may seem to vanish, while the emitted radiation slowly encodes its contents. Yet the radiation is initially thermal, offering no readable imprint. Several routes aim to resolve it. One family of ideas uses holography to place information on a boundary, so a complete description lives on a lower dimensional surface. In this line, the ADS/CFT correspondence provides a unitary description where the boundary theory preserves information. Complementarity posits that outside and inside observers each have valid, non-contradictory descriptions. The firewall thought experiment challenges the assumption of a smooth horizon, prompting fresh debate about what an infalling observer would experience. Other proposals point to soft hair, which envisions memory stored in gentle gravitational or other low-energy modes, and to fuzzball-like microstate geometries that replace the interior with a rich ensemble of quantum states. Remnants and late-time correlations in Hawking radiation also feature in the conversations. A useful diagnostic is the Page curve. The entanglement entropy of the radiation should rise as quanta are emitted and then fall as information is gradually released. This qualitative shape is what unitarity would require. While no experiment confirms it, these ideas frame how theorists model the flow of information through and beyond a black hole. The paradox in brief is the core tension between preserving quantum information and the thermal, seemingly structureless nature of Hawking radiation. The discussion remains open, pushing the boundaries of how gravity and quantum theory might fit together in extreme regimes. Infalling matter and exterior observers. From the perspective of an outside observer, the crossing of the event horizon by infalling matter never seems to happen in finite time. Light from the infalling object becomes gravely redshifted. Near the horizon, clocks run differently, and signals are stretched so that, to a distant detector, the object appears to hover at the boundary, growing dimmer as it recedes into the black hole's gravitational abyss. The exterior view preserves causality even as it freezes motion at the edge. In contrast, an observer who falls with the matter experiences the horizon as an ordinary seam in spacetime, with no local experiment detecting a boundary as they pass through. Tidal forces may wake you up only if you are near enough to the singularity. The equivalence principle guarantees that, locally, the physics inside a freely falling frame looks flat, so the crossing is unremarkable until extreme gravity changes the scenery. What you measure with your own senses is seamless. The tension comes from trying to reconcile these two views with quantum rules about information. Hawking radiation, born from quantum fluctuations near the horizon, is thermal. If the radiation carries away information, then an external observer could, in principle, learn something about the infalling matter without ever accessing the interior, which clashes with the expectation that the interior remains inviolate. No single observer can witness both descriptions in full. One proposed resolution is black hole complementarity, which posits that the exterior observers and the infalling observer's descriptions are both valid within their own causal patches, and no experiment can expose a contradiction. Another route entertains the firewall idea, suggesting a dramatic boundary to prevent information loss, but at the cost of violating the equivalence principle. The modern picture often invokes holography and ideas like the ADS/CFT correspondence, where a unitary quantum theory on the boundary encodes the bulk, hinting that information is not lost even as the geometry swallows it. Emerging notions such as quantum extremal surfaces and soft hair add nuance, offering routes to preserve information without obvious contradictions. The information paradox and entropy. Black holes carry entropy proportional to their event horizon area, a result that ties gravity to thermodynamics in a surprising way. Hawking radiation shows they can emit particles and slowly lose mass, so a black hole can evaporate. This is the setup for the information paradox, a conflict between general relativity, quantum mechanics, and thermodynamics. From semi-classical reasoning, the radiation is almost perfectly thermal and seems to erase the detailed information about what fell in. Entropy here acts as a tally of the quantum states that the horizon can encode. It is not simply disorder in a gas. It is a measure tied to entanglement across the horizon, linking geometry to quantum information. The Bekenstein-Hawking relation makes the link explicit and shows that entropy scales with area rather than volume. That area law behavior is what makes black holes unique laboratories for thinking about information. As pairs of particles form near the horizon, one falls in while its partner escapes. Radiation appears thermal because the pair is entangled with interior degrees of freedom. The remaining interior partner is beyond reach, so the radiation seems to carry no information. Page's insight proposes how unitarity might be preserved. The entropy of radiation should rise and then fall, producing a Page curve. Later developments use holography and gravity to compute entanglement islands, which capture information in early radiation, reconciling semi-classical gravity with unitary evolution. These calculations suggest information can be encoded in subtle correlations across radiative quanta, even if each quantum alone looks thermal. The idea is not that information travels faster than light, but that it emerges in the correlations among emitted quanta over the entire evaporation process. In practice, the paradox remains unsettled at a fundamental level. No experiment has directly observed black hole evaporation, but theoretical frameworks keep testing consistency. Analog systems, such as sonic or optical horizons, reproduce Hawking-like radiation and offer test beds for how information might be encoded in correlations. Ultimately, the information paradox acts as a guidepost for quantum gravity, steering discussions about the holographic principle and the true nature of spacetime. Proposed resolutions, firewalls, complementarity, and ER equals EPR. Hawking radiation appears thermal and seemingly erases information about matter that falls into a black hole, a tension with quantum mechanics that demands a resolution. Three broad paths have dominated the debate. Firewalls propose a dramatic departure. The horizon is not a gentle doorway, but a high-energy boundary that scrambles or destroys infalling information, ensuring the emitted radiation remains unitary. Complementarity reframes the problem. ER equals EPR offers a geometric connection between entanglement and spacetime by equating Einstein-Rosen bridges with entangled pairs, so that information can be encoded in the wormhole structure rather than hidden behind an ordinary interior. Firewalls rest on the AMPS argument, which exposes a tension between the monogamy of entanglement and the demand for unitarity. A late Hawking quantum would need to be entangled with both early radiation and interior modes unless a firewall disrupts one link. The result is a hot horizon. Critics warn that this breaks the equivalence principle and demands dramatic new physics at the horizon, implying an energetic barrier that an infalling observer would literally encounter. Proponents argue it preserves unitarity. In practice, the firewall proposal highlights a non-local clash. Maintaining information flow through radiation seems to require a breakdown of smooth spacetime for certain observers. Complementarity accommodates both viewpoints by letting outside observers and infalling observers inhabit different, non-contradictory descriptions of the same physics, so no single observer witnesses duplicated information. That is the core idea. The outside view treats the horizon as a machine for encoding information into Hawking quanta, while the infalling view preserves a seamless vacuum crossing the horizon, with the two pictures stitched together only by causal limitations. No one observer sees both pictures, The challenge is to formalize this as a consistent, local effective field theory and to show that no observer can operationally reveal a violation of the no-cloning rule, which lies at the heart of quantum information. ER equals EPR ties entanglement to geometry by proposing that every entangled pair is connected by a non-traversable wormhole, so information can be spread through a hidden geometric channel rather than purely through radiation. The enterprise rests on a concrete case in ADS/CFT. In the thermofield double state describing two entangled copies of a conformal field theory, the dual geometry contains a connected Einstein-Rosen bridge, providing a calculable laboratory for ER equals EPR ideas. The wormhole is not traversable, preserving causality. Supporters argue this viewpoint preserves unitarity and locality by reinterpreting information flow as a geometric question, while critics worry that it remains a conjecture whose generalization to realistic spacetimes is unsettled. Taken together, these resolutions map out complementary strategies. One insists on radical changes at the horizon, another on observer-based descriptions, and a third on a deep link between entanglement and spacetime that could reconcile information flow with geometric constraints. None is a final verdict yet. The landscape remains active, with researchers testing the consistency of these pictures against known principles, exploring simple models, and seeking a coherent synthesis. Observational windows and theoretical implications. Observational windows into black holes come from imaging the shadow of the event horizon, analyzing 10th-ray spectra from inner accretion flows, and listening to gravitational waves produced by violent mergers. The Event Horizon Telescope has produced resolved silhouettes of nearby supermassive black holes. In the 10th-ray band, timing and spectroscopy reveal how gas behaves as it spirals inward, tracing the inner edge of the disk and the gravitational redshift near the horizon. Gravitational waves offer a dynamic probe of spacetime curvature during merger and ring-down. Polarization measurements from near-horizon regions map magnetic field structures that influence accretion flows and jet launching, adding a diagnostic of the energetic environment just outside the horizon. The paradox arises from the contrast between matter crossing the horizon, where classical intuition says it vanishes, and quantum theory that demands information conservation. Hawking radiation is predicted to be thermal and apparently information-free. This tension fuels a flurry of ideas, from holographic dualities that encode bulk physics on a boundary to the notion that no-hair properties are compatible with information preservation. The island program and quantum extremal surfaces push the calculation toward a unitary page curve by including entanglement with early radiation. Such theoretical advances remain most concrete in controlled toy models and in the formal language of quantum gravity, while observational access to Hawking radiation from astrophysical holes remains out of reach. For observers, the practical implication is that tests must infer consistency between horizon-scale phenomena and unitarity through indirect signals. Direct Hawking radiation from stellar mass or supermassive black holes is effectively unobservable with current technology. Gravitational wave measurements of ring-down modes probe the immediate vicinity of the horizon and test no-hair expectations. Deviations could hint at new physics. Imaging shadows and lensing patterns with high resolution constrains the geometry of spacetime near the hole. Polarization and variability studies offer complementary avenues to assess how information might be encoded in the near-horizon quantum state, and how this could be reflected in spectra and timing. Looking ahead, improvements in very long baseline interferometry and space-based observatories promise sharper tests of horizon-scale structure and potentially subtle deviations from classical GR. Theorists anticipate that holographic ideas and island calculations will guide interpretations of future data. If a consistent picture emerges where information is preserved in radiation or in the entangled structure of the exterior, the observational windows will have nudged theory toward a quantum description of gravity that reconciles disappearance with existence. Until then, the paradox remains a guiding puzzle, shaping how we map the invisible edge where matter both vanishes and persists. Toward a synthesis of viewpoints. Hawking radiation appears nearly thermal, which makes the information problem in black holes feel stark and undeniable. The clash with quantum unitarity pushes researchers to seek a synthesis that respects both the semi-classical view and the full quantum description. A spectrum of perspectives, complementarity, holography, firewall arguments, fuzzball ideas, and soft hair proposals, offers complementary tools rather than competing verdicts. Each framework highlights a piece of the puzzle, how information can be encoded, preserved, and eventually retrieved without violating known physics in ordinary settings. The challenge is to build a coherent account that can operate smoothly across different regimes and observers. Complementarity provides a pragmatic way to think about observer-dependent descriptions. An outside observer can regard information as encoded in Hawking radiation in a way that appears unitary, while an infalling observer experiences no drama at the horizon and carries information in a local, causally disconnected sense. The proposal avoids a single global contradiction by allowing incompatible descriptions to coexist, restricted by what any single observer can measure. Meanwhile, the holographic principle and concrete realizations like ADS/CFT show that gravity in a bulk spacetime can be encoded in a non-gravitating boundary theory, with information preserved in the boundary degrees of freedom. The link between entanglement and geometry, exemplified by proposals that connect quantum information to spacetime structure, offers a natural route to unify non-local quantum correlations with emergent gravitational dynamics. Yet the interior of a black hole remains a delicate issue, because no single observer has access to both interior and full exterior data simultaneously. The island framework and related replica trick calculations bring a calculable angle to unitarity. When determining the entropy of radiation, certain regions behind the horizon are included in the entanglement calculation, effectively creating islands that belong to the radiation system. In representative models, this inclusion yields an entropy curve that halts its rise and mirrors a page-like behavior, aligning evaporation with information conservation while remaining compatible with semi-classical gravity in the outside region. The approach leans on quantum extremal surfaces and the gravitational path integral to produce results that resemble a full quantum gravity answer. It also dovetails with holographic intuition by treating parts of the spacetime behind the horizon as encoded in boundary data. Nevertheless, questions linger about the universality of islands and how these ideas translate to realistic astrophysical black holes beyond idealized setups. Toward a synthesis, a layered picture begins to take shape. Local, low-energy physics near the horizon can be described with effective field theory, while global information flow relies on non-local gravitational effects tied to holographic principles and entanglement structure. Soft hair provides a bookkeeping channel, allowing horizon degrees of freedom to imprint subtle correlations on radiation without requiring dramatic new dynamics for everyday observers. Fuzzball concepts recast the horizon as a collection of microstate geometries, offering a concrete microscopic picture that avoids a traditional horizon altogether. Islands offer a practical tool to compute entropy consistently with unitarity inside a semi-classical framework. A matured synthesis maps which theoretical tools apply in which regime and ensures their predictions align where their domains overlap. The aim is a shared dictionary that translates interior experiences into boundary data and radiation correlations, without forcing a single narrative to dominate. In this view, the paradox remains a guide to the structure of quantum gravity, not a dead end, and the path forward is to choreograph these viewpoints into a coherent, testable framework. That's the black hole paradox in a nutshell. Matter crosses the horizon and seems to disappear, yet quantum effects and Hawking radiation hint that something about it persists. The tension between what we know about gravity and what quantum theory says about information makes it feel like matter both vanishes and leaves a trace at the same time. It's a frontier where disappearance and persistence meet, inviting us to rethink how reality is stitched together. If you're watching this, you're probably curious about how deep questions like this connect to our understanding of the universe. The paradox isn't just fancy math. It's a prompt to imagine how information, space-time, and the laws of physics could be woven into a single, coherent picture. If you enjoyed the exploration, drop a like, subscribe, and share your thoughts in the comments. Your questions and ideas steer what we tackle next. In the next videos, we'll dive deeper into concepts like the holographic principle, ER equals EPR, and the firewall debate, and we'll look at what current and upcoming observations, from gravitational waves to horizon-scale imaging, could reveal about the fate of information. First, I'm excited to take the journey with you and to bring in fresh perspectives and discoveries as they come. See you soon.